Okay, so I will introduce you in this speech what exactly is machine learning and how it can, why it's important, I think, to solve psychological questions. And I try to make my talk very easy, or at least specifically designed to talk to psychologists. So I hope I hope the goal will be met. If there are things that you don't understand, don't hesitate to ask questions. So first, just a little presentation, but I already did it. So I'm doing freelance computer development and projects, managing and many things for a little more than 10 years. And I'm also studying psychology at the University of Paris. To start, I would like to introduce you to this guy, Frank Rosenblatt, that you probably never heard about it. But in the field of artificial intelligence, this guy is a legend. Why? Because he's the first one that tried to implement what we call an artificial neurons. He used the knowledge that we had in the 50s about how neurons works, and he implemented the same system with computers. And his aim was to make a system that could distinguish between two types of image. So imagine that you have image with cats, images with dogs, and then his system would be able to tell, okay, this one is a cat, this one is a dog. So it was the very first attempt to do that. And for the anecdotes, this guy was a psychologist. So it's interesting to know that the first who did that kind of work that we will see after more complex occurrences was a psychologist. So now I would like to tell you about my vision of psychology today. We try to understand things, but psychology is so complex. It's like it's so far from the laws of physics. There are so many different levels. There are the biology, there is the interactions between humans that make it so complex that it's hard to find the rules that are behind everything. So for me, what we are trying to do is we know things. We know that we know things, but we are limited by the accuracy of our theories. And I think the best way to see that is to see that in psychology and in therapies, we always have very small effect sizes for every type of treatments. For me, psychology tomorrow will be this. We have to go deeper. We will have to dig way deeper. But the tools that we are using today do not allow us to dig this deep. The idea is that we need some kind of big machines to excavate a lot of the grounds. And once we excavate all this ground, we will be able to find the structures as we did in the picture before. And the big machine that will excavate all this ground, for me, it's deep learning. Deep learning is a kind of machine learning. I will come to it a little after. First, I will just show you what's machine learning at its very basic form, because machine learning is actually used for many years, many dozens of years. And it's possible that you even use machine learning. Think about if you're using a computer with your data and you try to find correlations to calculate correlation coefficient, it's already machine learning. So this one is the most basic form. Imagine that you have an independent variables and you have a dependent variable. You just plot your values on a graph. And here you can see that it has a shape. And in fact, there is a line that kind of fits the data. And in this situation, what we say is that we have a correlation between the two variables. And the higher the coefficient number will be, the more the dots will be close to the line. This is the most basic form that we can do. And it's called linear regression because it's a line. But in fact, there are other type of relations between variables. It doesn't have to be linear. And one of the examples that I can give you is, imagine if you want to study the effect of sleep on feeling well during the day. What you'll find is probably something like, if you don't sleep, you'll feel bad. And then the more you sleep, the better you will be. But then if you sleep too much, there will be a point where you feel bad again. And this shows that it's not linear. It's not that the more you sleep, the better you'll be, but there is a kind of place where it's good, but if you go out of the range, it will be bad. And in fact, there are even more complex forms of relations. If you look at this graph, you see that if you just watch it, you see that it has there is a logic behind it. It appears to be a logic, but with a straight line, it's impossible to go close to it. Now, there is another type of machine learning that is very used, and usually, if you already heard about what we are doing nowadays with machine learning, it's prediction. Prediction could be a protein folding problem or recognizing images, that kind of stuff. It's called classification. So I made a little example. You can imagine that here I made an experiment and the data I have, it's to help people with depression. And at the very end, from the people that I tried the treatment with, some are getting better, some are not. And on the columns, you can imagine whatever. It could be the age, it could be the weight, could be questions like, do this person have close relations, close friends? Does this person exercise, and so on? And once you have many measures, then you can predict someone you didn't do the treatment to this person, but you know all the other characteristics, and then the algorithm can tell you if statistically, given every other people you try the treatment on, what's the probability that the treatment will work on this person, and how it works behind. It will try to do inferences between the variables. It can be complex inferences. Another type of machine learning use, it's called clusterization. It's how to make groups. For example, here I have dots. And then you can see, if you see this picture, you probably intuitively see that it looks like there are two groups and that those groups are different. In fact, it's what the algorithm does. It tries to find the more meaningful group. But here it's easy because there are only two variables. I have another example with 3 variables. As you can see, you can still do it. You can still recognize that they appear to be different types of people. But the thing is, this is with 3 variables. What happens when there are 4, 5 variables? It's just impossible to imagine because our brain cannot do that. It's not possible to put that on an image. So after 4 or 5 variables, it becomes very difficult. Another question that you would like to probably ask is, how many variables do we have usually? If we make a psychological experience, how many meaningful variables can we use, and how many are they? Answer is a lot, because what is a variable dimension could be anything that you measure. It could be physiological, anthropometrical, things about where the people live, the age, even the weather, because we all know how the weather is affecting our lives. And subjective measures are also a kind of variables. Any questions that you ask, for example, did you sleep last time? Did you sleep well? Do you eat? What are you eating? What is your diet? Do you have friends? What you're earning could also be a variable. And then there are other types of variables that we are not using today, such as neuronal imagery, because it's too complex, but we can do it with computer. And genetics, we could even say that if you want to study a population, maybe we could use the whole genome of everyone, because there is probably meaningful information into that, and so on. So deep learning, what is it? In a nutshell, deep learning, it's finding the best nonlinear model for either regression or classification. It's the example that I showed you before, the simple examples with the graph. Deep learning can do that, but can do it. It's the best tool that we have nowadays. We have many tools that tries to find meaning into the data, but deep learning, it's really the best. And why do we need it? Why do we need this best method to get the meaning out of the data? Because variables there are billions of variables, probably even more. The number of variables are so high that there is no other way to treat that many variables. Think about today when you do a study in psychology, usually how many variables do you have? Sometimes it's 3, sometimes it's rarely more than 10. But the fact is, life is so complicated. The people are so complicated. There are so many things that can interfere with everything that if you really want to understand to its fullest the laws that are behind them, there are probably billions of things that you need to take into account. And also many relationships between those variables, they're not linear. Finding a linear correlation between two things, it's the most simplest kind of relations. But there is no reason that it's this, that it will be enough to find really how everything is interfering with each others. And last point is that those variables are in fact influencing each other. For example, diet, exercising, anything that you can have in your life, it's always the result of many different other things. And so it's kind of easy to see. And how does it work in practice? Just by using computers. Actually, it could be done on a smartphone, but you only could do, you could not take billions of variables into account, but you already could take many into account. So from smartphone to supercomputers, you can use whatever you want depending on the complexity of what you're doing. And in fact, deep learning, it's only statistics using artificial neural network. So it's, in essence, it's the same thing that this guy Rosenblatt did 60, 70 years ago. It's simulating how neurons work using a computer. And the question you might ask is, how is simulating neurons, how can it do statistics? What's the relations between simulating neurons and using statistics? And to understand that, I would like to give you the example of the brain, because the brain, it's exactly that, it's a pile of neurons, many neurons. And what the brain do? Tries to predict the future, tries to infer things from his experience, and then it tries to predict what will happen. And that's how we can make choices. And that's also how we have some people who have problems into their modeling the brain. For example, that will think that there is a danger crossing the street when there is obviously not. Could be because of bad experience. But in fact, the brain is exactly that, a machine that does statistics to understand the world. And the way we could use deep learning will not be to simulate a brain, will not be to understand the world, but will be to make statistics about how people work. So what we try to do is not a model about how the world works, but how people work. And what can we do with this kind of model? We can answer this question that you may have already heard about. It's been formulated by Gordon Pohl in the 1969. It's what treatment by whom is most effective for this individual with that specific problem, under which set of circumstances, and how does it come about it? So the idea is that once we have a model that understand the most it can on people will be able to really help them on the most specific for it's really we will really be able to understand how to best help this specific person in this specific moment. And in practice, how does it work? We need lots of data. The more we can, there could be billions of different variables. It doesn't mean that we need billions of variables to do something that is good. It's possible that we need way less. But the more we have, and there is a consensus in the field of artificial intelligence, is whatever you're trying to do, the more data that you get, the more the accuracy that you will have. And it's because, of course, if, for example, you would like to understand how the world works, it's easy to imagine that you need the more possible data. And you don't just need the data about specific parts, but you would need data about everything. All this data will allow us to build a model of how people work. And just to put the emphasis on the model of how people work, it's what we are already doing in most of the papers that are published nowadays. It's just that the models are only taken a few variables into account. So the models are actually quite simple, but they have to be simple because we have to be able to understand them. But if we want it to be very powerful and more efficient, then we need to get a few steps above that. And once we have this model, how people work, then we can start to ask questions to this model. And this is where it gets interesting. And for example, this question could be, what are the best predictors of depression, anxiety, schizophrenia? What are the best predictors of helping someone who suffers from PTSD in this specific situation? Not PTSD in general, but it would be PTSD in this specific situation. Then there is something that I found interesting also, is it would be also possible to just put yourself, you measure yourself, and then you ask, given your own data, am I at risk of something? And then it's possible that the model would tell you, today you're okay, but we know from analyzing many people that you might be at high risk to have a depression period in a few months. And this is things that we could know in advance. And then we could also ask questions such as, can I mitigate it? Are there things that I can do in order to not have this depression event that I'm at risk in a few months? And then the model could tell you, from the people we already have data of, it looks like that the one who did this or that, they don't appear to have this depression period. So it's another type of question that we could ask. And also the question, what works on people with similar circumstances that I have myself or that your client have today? And what should we do to use all this thing? Of course, collect more data. This is really I think this is the main point of my presentation. It's that we need more data. And because science is rarely intuitive, and most of the time, the things that we discover in science were not the one that we had in mind first, but it's things that we found sometimes even by chance, or by looking at something else, we realized that, and then we got more ideas. And usually that's how it works. And also we should publish the raw data, because that's where all the information is. All the informations to help the people are in the raw data. If you don't publish it, then it's just us, we make our research, and then that's it. But we'll never have this ability of people in the future that we use our own data to realize new things, to discover things that we didn't even think about. And so we are, by not publishing the data, all of this would be close. And to have another example about, for example, compared to what we do today, in many papers we're using scales to measure. For example, we have an anxiety scale, we have depression scale. You can even think about IQ scales, all those scales that gives you a score at the end. And my point is that when you have a score, it's just a reflection of the answer of the people, but you already lost all the information that could be very meaningful for something else. Because, for example, if you have a depression scale, maybe there are some of the questions that would be important to know if it's one type of depression or another. And given this specific answer, we could direct the person to a better treatment. But since we only have the score, there is nothing we can do about it. And now I have a little warning. It's about what we are doing today, and that I think is not really good to discover new things. And the first one, the field is starting to get very aware of it. I read a few things about it. It's that the DSM categories, they're not great. Because, for example, let's take schizophrenia or things that are quite complex. And then we put many different people into a bag, and then we try to find a treatment, and then we use this treatment for everyone, and then we realize that on average, the effect size is very small. But it's possible that it's just the consequence of having put different people into this bag. It's possible that this treatment is very effective on one very specific kind of schizophrenia, but we cannot know it because we're using big groups. And we are also using groups in middle-level terms, like self-compassion. For example, I'm not saying that self-compassion is not useful to talk to clients in therapy, because it's important to talk the same language. And in this context, it's useful. But if you want to study self-compassion from a scientific point of view, you will always run into the first question that you ask is, how can we define self-compassion? And this is when things start to get bad, because then you will put different things in the bag called self-compassion. And every time you put things in a bag, every time you group things, you never know that if in fact it's really meaningful to have this group. Because it's not because we have intuitively ideas of how to group things. And in the case of self-compassion, it's very cultural. I think what you would put in self-compassion will depend a lot on the culture. And since you put different things in the same bag, it's not possible to get meaningful results out of it. Because what you would like to have is things that you can really use, such as, do you allow yourself to have some free time or some fun every once in a while? This is something that you can have. But self-compassion, since it's a bag of something, we are losing data and not possible to find good rules with such concepts. Now, of course, there are misuses, potential misuses to these techniques. First, error margins. There are always errors. It's never 100%. It will never be. It's already the case today, though. If you know that you have a treatment that works well for a certain type of people, you know that it's not always the case. You know that it's better to really understand the person, really, that's how the work in therapy. This will not change because you always have to be specific with a person, and because there's always errors. And the fact that we are using a more advanced model of statistics, deep learning, it will not at all fix this problem of errors. And also, we will know nothing about causality. We will know relations between things. We will know that something is in relation to something else, but we will never have information about causality. To have information about causality, you will still need to design very clever experiments in order to find out. Then things change. If you build today a model of how people work, and that you find that it works today, doesn't mean that in 20 years it will still work. Could even be less, even in 5 years, because things change. So it's a never-ending behavior, I would say, because you cannot just make a model and then use it for always. So it's important to have this in mind, to always update the model with new data. And also, it's a trap, I think, that we also have today. You could design a treatment that makes people better fast, but that in 2 months, it will not be effective anymore. This is also the type of problems that you can get with deep learning, because remember that deep learning, it's really at its most basis, it's statistics. It's using a better statistic model, but it will not solve all the other problems that we already face today. And I have some good news, actually. I read the ACBS task force report, and I've been very pleased to know that there are many things that are going in the right directions. So this is kind of cool. I don't think I will read it because I have a few pages about it, but it's mostly talking about we need more data. We need to find ways to make treatment that are more specific. Here we have many processes are non-linear. So there are many things that are already going in the right direction. This is cool. What's left to do once we use deep learning? As I told you before, since it's statistics, all the rest will still have to be done. And this is composed of designing clever experiments, researching about causality, still has to be done. Implementing the findings in therapy, it still has to be done. And all the theoretical work will never be done by a machine, because that's today it's completely out of reach to do that kind of things with machine learning. So it's not a silver bullet. It will not solve everything, but it will give way more substance to do the other work, I would say. And now before we end this, just for fun, I asked myself, oh, Jeff, how could you slow down research the most? If you could do anything, what would you decide so that you could slow down research? So that psychology will make a little bit of progress, but not that much, so that things will not change, and then we will be able to sit on our desk, not really working, but still advancing a little bit. And this is a little provocative, but then my answer would be: do not release the raw data, because that's how you slow down research. If you do not release the raw data, it slows everything down. And thank you very much.